Hi, welcome back. This is a screencast on how to conduct regression models. In this video, I'm going to walk you through conducting a series of unadjusted linear regressions. We'll also talk about the various cells and data you need to pull out of the output in Spss, where to put it in a table. And then we'll do the same thing for logistic regression, and then I will go through some explanations. All right. So just to start, kind of what's happening with Miniproject 3 is we're going to conduct 6 linear regression models. All right. 5 of them are going to be unadjusted, which means that they are simply an independent variable with a dependent variable. So 1 IB and 1 DB. Okay. We're going to do this for all 5 of our independent variables, and then we're going to have a final multivariable regression model which has all the independent variables in it. Okay. Now, what we're doing here is we're looking at what the relationship is between an independent variable and a dependent variable in a linear model, and we get a sense of what it is, and then we'll also see what it is when we put all the variables into a full model together. And when we do that, we're essentially taking into account all the other things that could be affecting our particular, the relationship that we're looking at with our independent variable and our dependent variable. So we start off, we do an unadjusted model, and we might do something like percent of residents with no high school diploma and a cancer mortality rate, right? And then the coefficient we get is essentially a representation of that sort of statistical problem, right? And we'd be looking for a way to interpret it, like every 1 unit increase or 1% increase in the percent of residents without a high school diploma increases the cancer mortality rate by, 1 death per 100,000 or 1 death per 100,000, something like that. All right, that's what we get out of the linear model. And then in a multivariable sense, when we have all the variables together, we can say, all right, this is a coefficient, this is what the relationship is, comma, while controlling for or accounting for the other independent variables in this model. It's not really as complicated as it seems. It's actually pretty straightforward. The other thing we get out of a linear regression is we get an estimate of the variance in the dependent variable that is explained. Now, the textbook, I believe, refers to this as the coefficient of determination. And what that is simply sort of referring to is it is the proportion of variation in our dependent variable that is accounted for or explained by the variables that are in the model, the independent variables that are in the model. So if you have, one variable, we'd say, this is the amount of variation in the dependent variable as explained by, percentage of residents without a high school diploma. And then ideally, you kind of and then ideally what you get is you say, with all of the variables in your model, comparing them head to head. So you could say percent of residents without a high school diploma percent of residents without a high school diploma explains more of the variation in cancer rates than the Gini coefficient or per capita income, something like that. Okay. With the logistic models, what we're attempting to do is we're trying to estimate the odds of our dependent variable happening. Now, it's a little strange for us because you have a dependent variable that you've been working with, and it's linear. It's our interval or ratio level measure. It's a rate, okay, or a percentage. And so, that doesn't work in a linear model. So the first thing we have to do when we start doing a logistic, that doesn't work in the, so that interval or continuous ratio level measure doesn't work for a logistic model. And so the first thing we have to do is we have to make a binary measure. We have to make something that's 1 and 0, okay? Now, there's lots of different ways to do it, and everybody we could have a conversation about which is the best way. But it's kind of like, it doesn't really matter for this project because, this is just to get you to learn how to do it. So for us, what we're going to be looking to do is we're going to we're going to choose some type of cut point on that measure and make a binary measure for it. So we'll say any community area that has an infant mortality rate that's higher than blah is going to be a 1. Every community area that has an infant mortality rate that's lower than that is going to be a 0. And then instead of doing a logistic regression on those infant mortality rates, we are instead doing it on the likelihood of a community area having an infant mortality rate that's greater than 5.9 deaths per 1,000 births. Now, where did I get 5.9 deaths per 1,000 births? I looked up what the average infant mortality rates were for 2012 to 2016, and I'm basing, that's for nationally, and I'm basing that, my number on that. So I'm going to say basically the likelihood of a community area having an infant mortality rate that is higher than the national average. That's my dependent variable. Okay, it's going to be 1 or 0. So that is that. The regression modeling isn't too difficult here. It's pretty straightforward. What can be a little tricky is knowing which statistics to pull out of the output to put into our table. And so towards the end of the screencast, we'll get into a lot more of that. All right, so here's just some things that we're doing here. I'm not going to read this to you because you're in college, and I feel like you could probably read it to yourself. This is the linear regression table that we're going to be working with. And so after you do your 6 regressions, you're going to put the statistics in each of the spaces that I've marked here. And then for Miniproject 3, you'll be writing up an explanation of what you did and your results in, I think, a handful, 1 to 3 paragraphs, maybe 1 to 2 paragraphs. For logistic regression, same, although the table is a little different because we're dealing with odds ratios, and so there's fewer cells that we want to capture, but it's largely the same sort of process. Okay, so let's get into it. We've got written instructions along with screenshots so you can follow along. We're going to start, before we do anything else, by executing all of the syntax that we've done so far. All right, up to now we need to have all of this done. And that is because we want to be working with the measures that we made, which were simply copies of the originals. And that's, kind of where we're going to be starting from. Now, going forward with Miniproject 3, we're not going to be working with the north side or north side, south side, west side variables anymore. That was for Miniproject 2 to help us do 2 category and 3 category testing, but we're past it now. Okay. So let me see if I can go split screen here. And, what we want to do for the regression is we're going to click on Analyze, and we're going to click on Regression. And we're going to start with a linear model. So we're going to go ahead and click Linear. All right. Once again, all the regressions are going to look a little different based on the different type that you do. So if you get something that does not look like this, then you just need to shut down that regression and go find the variable that you're looking for. Okay, or go find the regression that you're looking for. So we're going to start with average IMR 2012-2016. All right, we're doing a linear regression first. So we're going to start with that as our dependent variable. All right, next up, we're going to take the average percent of foreign born and move it into the independent variable window. Now, that's it. We don't need to do anything else here. All right, so let me see if I can get this back. And we're going to take this this syntax, and we're going to go ahead and put it into our syntax window. All right. So blam. Okay. Now that we've done that, I'm actually going to paste it a few more times because I'm not really a big fan of using the drop-down menu, so I would rather just paste a bunch of these in place and then go out and swap out the IVs for DVs, or IVs for the other IVs. Okay, so let's go ahead and hide that. All right, and look at what we're working with here. Now, in regression modeling in SPSS, we get a couple different things. We get a variables entered slash removed, we get a model summary table, we get an Anova, that is the Anova, the one that we started working with in previous chapters. I want to say it was like chapter 8, maybe chapter 10. It's the same Anova, the analysis of variance. And then we have our coefficients. All right. So the first table tells us variables that were entered or removed from the model. Now, this isn't going to make a lot of sense for you because you only put one variable in. But sometimes people would have a model where they've got maybe 20 or 30 variables in. And one thing that these statistical packages will do is if there are two variables that are perfectly correlated, they will kick one of the variables out. Okay, so this is just a little warning message, this variable's entered slash removed, to let us know whether or not any of our variables were kicked out of the model. Okay, you shouldn't have any variables kicked out of your model because none of your variables are going to be perfectly correlated with each other. All right, so you can largely ignore this variable's entered slash removed table. Next up is the model summary. Okay, in this space we get an adjusted R squared. Now, the adjusted R squared and the R squared are kind of, they're sibling concepts, right? Both are a proportion of variance that is explained, okay? Now, the problem is that the adjusted R square takes into account the number of variables in the model, all right? So, because there is this sort of tendency slash standard of succinct statistical models, the idea with statistics is that you have the fewest number of variables necessary, okay? So models that have fewer variables are rewarded by bumps or, let me say, smaller than necessary decreases in the adjusted R squared, okay? So kind of think about it in this way. We want efficient models, right? If a model can explain 40% of the variance with 2 variables, that is obviously better than a model that explains 40% of variance with 10 variables, okay? So one way to sort of account for the differences, the differing amounts of variation that is explained by the number of variables in the model is with this adjusted R squared. So the adjusted R squared is the percentage that we want to, or the number that we want to get out of this model summary table. Now, our coefficient here is 0.429, and what that is saying to us is about 43% of the variation in infant mortality rates at the community level is explained by community percentages of foreign-born residents. Okay, just it's kind of interesting. Then I get this Anova table, and the Anova table is simply telling us whether or not this model is statistically significant. Okay, does this model do a better job predicting infant mortality rates for community areas than a model with no, let me rephrase. Does the Anova here asks, does this model do a better job predicting infant mortality rates at the community level than a model with no predictors? Okay, and it does. It does a significantly better job. All right. And with this, we don't have to like go into a lot of explanation here. Just noting that it's significant, which means that the sig value right here is 0.05 or less. That's all we need to kind of take note of. And then the last table we see is our coefficients table. And this gives us 2 sort of rows of data. One is the constant and one is the data for our variable. Now the constant is kind of it's a little bit of a goofy concept, but essentially it is the amount of our dependent variable for all of our community areas if average percent of foreign-born was 0%. Okay, so if we could make all the community areas in Chicago have an infant mortality rate of, have an average percent of foreign-born percentage of 0%, we would expect that the infant mortality rate in these community areas would on average be 11.88 deaths per 1,000 births. It is significant at the 0.05 level, which is to say, like, it's significant here at 0.000, which is less than 0.05. And so like that's good to know. But the constant, we don't spend a lot of time interpreting it, mostly because it's sort of conditional on holding the independent variables at 0. And that's very rare, like you don't have that. And it's a sort of a theoretical or a hypothetical exercise. So we don't put a lot of time, attention, or effort into interpreting stuff about the constant. We do care about the unstandardized beta and the significance value, okay? What this unstandardized beta tells us is that every 1 unit increase in average percent of foreign-born decreases a community level's infant mortality rate by 0.203, okay? The direction here is important. That tells us the nature of the relationship, whether it increases with a positive value or decreases with a negative value. It is significant at the 0.001 level. So we have a probability of less than 0.001 that these results were achieved by chance. Meaning we have a pretty good idea, or we have pretty good evidence that this is a legitimate relationship that we are documenting here. Okay? So that's how you interpret, all right? Remember, variables entered, removed, we don't worry a whole lot about. We just want to make sure that the variables that we intended to enter are still in the model, and check to make sure that they didn't get bumped into the variables removed column. The model summary, we are interested in the adjusted R-squared. Okay, that's telling us the proportion or the amount of variation in our dependent variable that is explained by the independent variables in our model. Since there's only one variable in our model, this is a proportion of variation in infant mortality rates that is explained by percentage of residents that are foreign-born. Okay, so almost 43%. And then our ANOVA, we're simply looking to see if this model is significant. It is. We determine that by the significance column here. It's 0.000, which means that there is. So what we have in this final part of the table is a constant, the unstandardized beta for that, which, you know, we don't really spend a lot of time talking about it. We don't explain it. It would be useful if we were going to be writing out regression formulas. I mean, we could use, that would be the starting point. Like, we get that plus the coefficient, and we'd be able to predict an amount of infant mortality for a community area with 10% foreign-born residents, or 20% foreign-born residents, or 50% foreign-born residents. But that's very, that's sort of procedure and process is very, you know, it's kind of inside baseball, and there'd be very few circumstances in which you would want to do that. For the most part, we just say, you know, that every 1 unit increase in community level or community's percent of foreign-born residents decreases the infant mortality rate by by 0.203 deaths per thousand births, and that is significant. All right, so that's great. Let's go back to our syntax and see if we can speed this along. All right. So let me also get my data sheet available. That way we can kind of just like speed this up just a scooch. All right, go variable view. All right, so we did foreign-born, and now let's do non-Hispanic Black. Here, for this one here. Oops. I just didn't copy. All right, so non-Hispanic Black, and then Gini coefficients. Oh, you know what? I am off. I'm off the rails here. Hold on a second. I don't know what I'm doing. All right, so non-Hispanic Black goes here. Gini coefficient goes here. Per capita income goes here. And then no high school diploma goes here. Okay, so we're going to run these models 2, 3, 4, and 5 here. Gini coefficient. Oh, you know what? I somehow didn't get per capita income. I was dumb. All right. Paste. And I want to keep it in order because I am that extra. So let's take this guy and bring it down. Okay. So our order goes foreign born, non-Hispanic black, Gini coefficient, per capita income, no high school diploma. Cool. So we're going to take, we're going to highlight models 2, 3, 4, and 5 and run these. And we'll walk through the interpretation of a couple of, let's do one more, okay? So let's go with this guy right here, the per capita income measure. All right, looking at the variables entered, removed, there no variables removed, so that's good. The adjusted R-square for per capita income is 0.174. That means about 17.4% of the variation in community level infant mortality rates is explained by community per capita income. Okay, it is significant. This Anova model shows that it is significant at a p-value that's less than 0.001. Meaning that there is a very small probability that these results were achieved by chance. This is a likely a legitimate or real relationship that we're looking at. For the coefficients part of this, we have if we're able to make every community area have a per capita income of 0, the infant mortality rate, the average infant mortality rates would be 11.39 deaths per 1,000 births. Which is, it's high, but, we don't care too much about the constant row. We are much more interested in the per capita income coefficient. So every 1 unit increase in per capita income, which is to say every $1 increase in per capita income, raises the infant mortality rate by 0.000 deaths per 1,000 births. It is significant. It is significant at a p-value of less than 0.001. This gets us to another really important concept when we're trying to interpret and explain statistics. Just because something is significant does not mean that it is important. What this regression tells us is that every $1 increase in per capita income raises infant mortality rates by 0.000 deaths per 1,000 births. Okay? Significant, yes. Important, no. This doesn't say anything. Okay, so as a measure, because it has this sort of very tiny coefficient here, it's difficult for us to say a lot about what's going on with per capita income. It doesn't seem to increase or decrease the infant mortality rates at the community level. So this is going to be kind of tricky to interpret. And you can say in your interpretation, you could say, while this is a significant relationship or while this is a significant association, it is not meaningful, or it is meaningless. Okay, that's fine too. All right. So for the third or the last model here, this is for no high school diploma. No variables were removed, so that's good. We get an adjusted R-squared of negative. Okay, so that should just tell you off the bat that this is not a great variable to be explaining infant mortality rates. We have here a number that's less than 0, and so the idea of the adjusted R-square is that it should be a proportion or a percent. So, like, proportions and percents work. Negative percents, negative proportions tell you something very different. If we have that sort of strict interpretation here, we could say that 0.12% of the So as a percentage explaining of the variability in community level infant mortality rates, the percentage of a community area with no high school diploma does not do a very good job explaining variation. It just doesn't. So we could be like, all right, so that's not great. Let's see what it looks like in our model. Well, the model's not significant. So we have a significance value of 0.794. Remember, that's above our threshold of 0.05. So this model is not significant. All right, which is fine. Let's see what the coefficients are, because sometimes the model might not be significant, but the coefficients are. And we have the same. Down here we have a situation where the significance value is greater than 0.05, so we would determine that this was not a significant relationship or not a significant association. So when you have a significance value that's greater than 0.05, you don't have to do anything further with it. You can just simply say the average percent of residents without a high school diploma was not significantly related to infant mortality rates in Chicago community areas. That's all you got to say. All right. We don't go into any more detail. We don't extrapolate for coefficients that are not significant. So that is that. That's the explanation. All right. So let's pivot for a tiny moment and look at what we need to do for our full model here. Okay. So in the full model, we're going to do another linear regression, but we're going to add all of our variables to it. Okay, and I don't know what I'm doing spelling regressions like that. That's not me. And in order to do that, we can, to do the full model, we can do it a couple different ways. We can simply just add all of the additional variables to our model, our syntax. We just add them down here on the bottom row. All right, so we could do that. Or we could just go back to the drop-down menu and do that as well. That's fine. Linear regression. Since it's already here, let's go back and add these. So we've got non-Hispanic blacks, we've got Gini coefficient, we've got per capita income, we've got average percent of residents without a high school diploma. And voila. Okay, so you definitely want to make sure we get the syntax and put that in our file. And paste that. Okay. And now let's have a look at what we're looking at, what these variables do. Again, no variables removed, so that's good. All right. In the model summary, we have an adjusted R-square of 0.737. That's good. That's nice. Okay, about 73% of the variation in community infant mortality rates in Chicago is explained by average percent foreign born, per capita income, Gini coefficient, the percentage of community areas, percentage of non-Hispanic blacks in the community area, and then also the percentage of foreign born residents. So that's substantial. I mean, this is the adjusted R-square is going to range from 0 to 1. And so the closer to 1, the sort of better your model is, right? And then, not surprisingly, the Anova results show that this is a significant model. Nobody was surprised by that. And then if we look at the fully adjusted model, which is what's going on here, we have our coefficients in the table, and we also have our significance values. Again, we're only going to focus on the significance values that are less than 0.05. So in this case, we'd focus on non-Hispanic black, the Gini coefficient, and that is it. Okay, so there's kind of a couple different things going on here. So we have these two findings that every 1 unit increase in the percentage of non-Hispanic blacks in a neighborhood raises the infant mortality rate by 0.092. Okay, and that is significant. The other finding here is that the every 1 unit increase in the Gini coefficient increases the infant mortality rate by 0.146. Okay, because that's significant because the sig value is less than 0.05. So those are two findings we could say here. But what's also interesting about this is that average percent of foreign born and average per capita income, they become non-significant. Okay, these were significant in unadjusted models, but they are now non-significant. Okay, or they're just not significant. So what we could say is that when that happens, part of the initial relationship between percent foreign born and infant mortality rates in Chicago community areas was accounted for by these other things. So non-Hispanic Black, Gini coefficient, per capita income, and the percent of residents without a high school diploma. And same with per capita income. Remember, per capita income was that finding where it was significant, but it was the coefficient was 0.000. And this number right here is less than 0.0. It is not significant. So we're not going to spend a lot of time interpreting that. But the initial relationship that we were unimpressed with because the coefficient was 0.000 goes away when we include percent high school without a diploma, Gini coefficient, non-Hispanic Blacks, and percent foreign born. Okay. Now remember, this is very social sciencey, all right? If you have additional models in a variable, you are saying that part of the relationship between my independent variable and my dependent variable may be accounted for by the presence of another independent variable. That's what you're doing here, okay? And when your coefficients change, when they change direction, when they get bigger, when they get smaller, they become not significant. That is something, and that's what you should talk about, okay? We're not going to talk a lot about the coefficients that are not significant, other than to say initial unadjusted relationship between blah and blah goes away in the final model, indicating that at least some of that sort of association was due to these other variables. Okay, it is complicated. This is not easy, and so it's just important to kind of definitely have a good idea of what these coefficients are and what they mean for your interpretation. Okay. Now, before we move on, let's take a look at the table. Okay, put this, go split screen again. And, oh, you know what? It's up here instead. Okay, so for the linear regression, this final model that we just did, that was for model 6. Okay, so we're going to start by putting the coefficient in here for our IV. And we could play, there's definitely places to modify this. So we change this out to percent foreign born. Okay, the coefficient was negative 0.06, and that was, let's see, it was not significant, so we're not gonna have the stars here. The standard error for that coefficient was 0.039. 0.039. Okay. The constant for this is going to be in the bottom row here. So let's grab this one. It's going to be negative 4.061. And we're going to grab the standard error, which is 5.203. And then if I remember correctly, this we need model significance. We're going to take that from the Anova table. And this is going to be 0.000. And then for the adjusted R squared, this comes from the model summary table. It's going to be 0.737. Okay, so that's that part of it. Let's get the rest of these coefficients in here. IV2, that was average percent of non-Hispanic Blacks. That was 0.092. And the coefficient was 0.016. Okay, so we'll go percent non-Hispanic Black. Okay, this one was only significant at, non-Hispanic Black was significant at the 0.000 level, so we're going to keep the 3 stars in. As you can see at the bottom of this table, 3 stars pertains to p-values that are less than 0.001, less than or equal. Okay, so next we have IV3. This is going to be Gini coefficients. And then in the full model, the Gini coefficient was 0.146. The standard error was, oops, I am off the rails. Let me take a look here. Standard error 0.146 would be 0.71. All right, and then we're going to double check. Gini coefficient was significant at the 0.04 level. So that's less than 0.05, so it's going to only get 1 star. Okay, again, we're basing that on the bottom row of this table. That's like what we're working with. All right, and then for the fourth variable, this was per capita income. This coefficient was, oh, it's small. Like, this is a scientific number. You can actually just go to Google and search for whatever this would be. But I just know it's small. It's, since I'm carrying it only to 3 decimal places, like my 0.1617 would be behind 5 zeros, because that's how scientific notation works. This standard error is going to be zeros. And then, if I remember correctly, this is the per capita income. It is not significant in this full model. It goes out to 0.623. So we got to make sure all the stars come off of it. Okay, and then IV5, which is percent of residents without high school degree. Okay, and the coefficient for this is 0.09. 0.09, and it was not significant, right? Yeah, the significance value is greater than 0.05, so it doesn't even get 1 star, which is fine. Nice. Okay, I'm going to take out that extra space there. And the standard error for high school diploma is going to be 0.051. Okay, so that is how you do the full model. And then for model 4, which is going to be on percent of high school residents without a high school, or percent of residents without a high school degree, I would go in here and say, all right, what's the constant? The constant over here is 7.785. Standard error is 1.028. 1.028. The model significance here is 0.794. 0.794. Adjusted R square is, that's that one that's negative 0.012. All right. And then the coefficient is 0.013. And this one was not significant because the significance value is 0.794. So 0.794. Oh, I just need to take out the stars here. I was getting ready to type that in. Like, JBR, what are you doing? Okay, standard error in this situation is 0.049. 0.049. Okay, I need a standard error for my constant. It's going to be 1.028. Oh, I just put this last one in the wrong place. It's fine. I can fix it. All right. So that's how you do that. So this is models 5 and 6 done. No stars for the coefficient. And then we just keep it moving. Go back to per capita income and do the same. Okay. Now, I have included in the course module a couple of PDFs that talk about how to interpret these coefficients. And so I definitely, if you're All right, so had a minor problem with my recording in the one of many times I've done this today. So I have a 2 monitor setup plus my laptop that they're connected to. And so I have a Surface Pro, and I grabbed it to draw on the screen and talk. And in doing so, it completely jacked up the audio. So I'm going to start over with the logistic regression part of this, and I apologize ahead of time if I repeat a bit or I come across as a little uneven or whatever. Okay, that's just what we're working with. So I ended last segment letting you know that I have a couple of PDFs that I've created that will be in the course module for more detailed explanations on how to interpret the different parts of the linear regression output. We are going to take a minute now and do the same for logistic regression. So logistic regression, we start by making our binary measure. Again, you know, how I got my binary measure was that I just looked up what the U.S. infant mortality rates were from 2012 to 2016, and then I calculated an average with the calculator on my computer. And so that average was 5.90 deaths per 1,000 births. So with that, I created this new measure with IMR as such. Okay, now I will caution you and say don't tune in and out of this recording and decide, oh, you're just going to use the same numbers for your cancer measure, because that doesn't work. You won't get a number that varies, and the most important thing for a dependent variable is that you have something that varies. So do make sure that you're using a cut point or a threshold for your dependent variable that makes sense. All right, so let's go ahead and get this binary measure created. I've got about 44.2% of the community areas in Chicago had an IMR that was less than the national average of 5.9 deaths per 1,000 births. 55.8% had an IMR that was more. All right, so now let's start with the logistic regression. Okay, so the first thing, we're going to get to that by going analyze and then drop down to regression and binary logistic. And just a reminder, if you do this and you get something different, you get something that looks a little different, it's likely that you just clicked on the wrong regression. So don't send me a panicked email until you figure out if you are using the right regression, because that's just silly. Okay, so I've got my dependent variable binary IMR in here. We really do want to make sure we get that binary measure in, because if you use the non-binary, the continuous or interval level measure, your regressions are going to be messed up. So, and then our new foreign-born measure, new, I mean, it's not really new, it never left. It's always been here since Miniproject 1. So that's what we're using. We're using the one that we made, not the original. The original is forbor underscore 2012 underscore 2016. Mine doesn't have any underscores. That's the one I created. Okay, so we're going to go ahead and do this part. And we get a bunch of output with logistic regression. We get this sort of case processing summary. This is just a check to make sure that there aren't like excessive missing cases here. Several of you contacted me to let me know that some of your variables were missing values for 1 or 2 community areas, and that's fine, it's okay. We wouldn't want to have a case where you have something like 68 or 69 missing cases. Okay, so just, you don't even have to do anything with it, just double check it, look at it, be like, okay, so I have no missing cases, great. The dependent variable encoding, we don't need to do a lot with that, it's just letting us know how our variables are coded. 1 is for communities that have IMRs greater than 5.9, and 0 is for communities that have IMRs that are less than 5.9. The first block here, there's block 0 and block 1. Basically ignore everything in block 0. That's just an excessive amount of output from SPSS that we don't even need to mess with. The next part is this omnibus test of model coefficients. We can largely ignore that. The sort of meat and potatoes of the logistic output is going to be the model summary table, the classification table, and the variables in the equation. Now in the model summary table, this is a statistic. It's like an R squared. It's like an R squared. It's not really an R squared. You can't, Logistic doesn't lend itself to doing the, coefficient of determination. So what you get is these two things that these individual people, these theorists and mathematicians and statisticians came up with as a sort of pseudo R squared, a fake R squared. So we've got one Nagle-Kirky R square and the Cox-and-Snell R squared. We're not going to get too concerned about the differences between them. You just stick to one and interpret it if you're going to put a lot of weight on them when you're looking at your statistics. I don't think it's a good idea to do that with either, because it's kind of like arguing about the color of the tooth fairy's wings. It's like, okay, we can do that, but I mean, as long as we're all aware that this is, this is an exercise in futility, right? So the same thing. Like we can have a conversation about what it could mean, but it doesn't really mean an actual coefficient of determination. If it did, though, if we believed this, if this were an actually useful measure, we would say that Nagle-Kirky R square shows that about 20% of the variation in the odds of having an IMR over 5.9 deaths per thousand births is explained by the average percent of foreign-born residents. Okay, so that's that. This classification table, we're not going to worry too much about it. It is just a little 2x2 table that we can look at to see, what was observed versus what was predicted. Okay, so what was observed was actually what did we see in our data, and what was predicted is what we would see if there was a relationship between these two variables. So there were 33 community areas that were predicted to have an IMR over 5.9 and who actually were observed having an IMR over 5.9. There were 14 community areas that were predicted to have an IMR over 5.9. But who ended up having an IMR less than 5.9. Okay, and so on and so forth. Lastly is our variables in the equation. We've got our beta coefficient, standard error, Wald statistic, degrees of freedom, significance, and exponentiated B's. Okay, so just to recap, we don't need to worry about the standard error, the Wald statistic, or the degrees of freedom for the interpretation part. I'm going to ask you, I think, to pull the standard error out and put it in a table, but that's about it, okay? The problem with logistic regression is it gives you a coefficient. In this case, for average percent of foreign-born residents, it's negative 0.07. However, it's a kind of a strange number to talk about because it's the exponentiated odds, okay? For the log odds. I don't know. It's weird, right? So no one ever interprets the beta coefficient. All right, that's this thing. Everybody always interprets the odds ratio, which is this thing, okay? Now the odds ratio is you take the beta and then you exponentiate it, okay? So you take negative 0.072 and do an exponent and you get an odds ratio of 0.931. Okay, so that is what we always look at and interpret. In addition to that, we also look at the significance column. In this case, it's right here, it's 0.000, indicating that we have a p-value of less than 0.001. So there is a probability of 0.001 or less that these results were achieved by chance. Now, I'm going to get back to explaining this odds ratio in a second. I want to get through the rest of my logistic output so you could see what it is that we're going to be working with. So that's our first one. Let's run all the others. Okay. All right. So kind of the same deal with the output. It's probably not going to be very useful for me to whip through this and explain it, but here we go. So by per capita income, this is Gini coefficient. This is average percent of non-Hispanic blacks. Okay, so the second of our variables, the percent of non-Hispanic blacks in a community area. Again, the first part of the logistic output we don't care about. It's everything in block 0, right? Whatever, we don't care. In terms of a percent of variation in the odds of a community having an IMR greater than 5.90 deaths per thousand births, Albuquerque was slightly higher, suggesting that about 54.5% of the odds of a community area having more than 5.9 deaths per thousand births is explained by the average percent of non-Hispanic blacks in that community area. Okay, we've got our classification table, and then we have our variables in the equation. Again, we don't care about the B here. It's nice that it's there, but we don't really have a whole lot to say about it. It is significant, and so we have an odds ratio of 1.05. So every 1 unit increase in the percent of non-Hispanic blacks in a community area raises the odds ratio of that community area having an IMR greater than 5.9 deaths per thousand births by 1.05. Okay. I'm going to kind of whip through the last of these so that I can get to the part where I kind of spell this out and give you a little bit better way to interpret the odds ratio. For the Gini coefficient, we have a Albuquerque of 0.239, so about 23.9% of the variation in the odds of having an IMR higher than a national average is explained by the average Gini coefficient for community area. And then we have, it is significant, so at the 0.001 level, so we have a probability of 0.001 that these results were achieved by accident or by chance. We are mostly interested in the odds ratio, which is the EXPB portion down here. And so that we find every 1 unit increase in the Gini coefficient decreases the odds of having a high or having an IMR that's higher than the national average by about 19%. Now I'm going to explain this more in a second. Okay, so don't get too worked up yet. All right, I am going to get to it. We've got a per capita income here, again, largely ignoring everything in the 0, in block 0. We're going to get to Albuquerque R squared. So for per capita income, about 15.3% of the variation in the odds of communities having an IMR that's greater than the national average is explained by the per capita income. Our odds ratio is 1.000, and the significance level is 0.008. Now, so this is significant at the 0.01 level, which is nice. But for the odds ratio, it's 1.00, which means equal odds. So if you think about it, if somebody has 100% of the apples that you have, how many apples do they have? They have the same number of apples. Okay, so if somebody has 100% of something that another person has, it's the same amount. That translates to odds ratios. Okay, so if there's a a 1.00 odds of something happening, then there's a equal chance of it happening versus not. It's not versus not. There's an equal odds of something happening with an odds ratio of 1.00. So what this is telling us is that every dollar increase in per capita income increases the odds of a community area having a IMR higher than 5.90 deaths per thousand births by 0, because there's no additional increase. All right, 1.00 is the same. It's equal odds, so there's no additional odds that are gained by increasing per capita income. Okay, so case processing 00, get to our block 1 here. We've got about 1.7% of the variation in infant mortality rates in the odds of communities having IMRs greater than the national average. about 1.7% is explained by the average percent of community area of residents without a high school degree. Okay, so very small percent. We've got our classification table again, yay, and then our variables in the equation. Now this significance level, 0.323, is greater than our threshold for alpha, which is 0.05. So automatically off the bat, like, this is not significant. So we're not going to talk a lot about it. We're not going to go into detail about what this odds ratio means because it is not significant. Okay. All right. So that gets us to the full model. And the full model is a multiple variable regression model. And it has a Nagle-Kirky R-squared of 0.612. So if we believed in these pseudo R-squares, we would say that about 61% of the variation in the odds of a community area having an IMR greater than the national average is explained by percent foreign born, percent black, Gini coefficient, per capita income, and average percent of residents without a high school diploma. Okay, now for us, what this means, looking at this regression table, we've got significance values, 0.704, not significant, 0.002 is significant, 0.065, not significant because it's greater than 0.05, 0.229, also not significant because it's greater than 0.05, 0.023 is less than 0.05, so it's significant. So of the 5 variables that were included in our unadjusted models, of the 5 variables included in the fully adjusted model, only the average percent of non-Hispanic blacks and the average percent of residents without a high school diploma were significantly related to the odds of a community area having an IMR greater than the national average. Okay. The rest of them, you could say average percent foreign born, Gini coefficient, per capita income, were not significantly related to the odds of a community area having an IMR greater than the national average. Okay, so we're going to go to my OneNote document. And let's have a look at linear regression. So this document, you'll have a PDF. This is a PDF of this is what you'll see in the course module. I've just basically written down all of the sort of context for all of these individual statistics and what we need to focus on and what we don't need to focus on. For the regression tables in Miniproject 3, we do have to pull out some of the coefficients. I've already started here. Let me pivot back and to our output. Okay, so these are all the linear models. Okay, linear. Okay, so in I think I already did this. Yeah, I already did this with linear. I'm really tired. I don't know what I'm doing. So I did this with linear already. I pulled out the coefficients and put them into tables. The one for logistic, I don't think I actually did. So let's take a look. So for the percent foreign born, the odds ratio is 0.983. If it were significant, we would put asterisks here, 1 to 3. And if you have a hard time remembering which ones you should use, they're down here at the bottom of the table. The next one is percent black. We got 1.084 here. And the significance level was 0.002, which is larger than our 0.001 threshold. So it automatically gets a 0.01. So 2 stars there. We also get 1.188 and 1.00, neither of which has a star for significance. 1.144 is the coefficient for non-high school diploma. and then because it's significant at the 0.023 level, that clears it for 0.05. We grab the constant here, okay, negative 15.661, throw it in there. It is significant at the 0.05 level, so it gets 1 star, and then we get the R squared value out of the NAGL or the model summary space there, okay? And then, so for odds ratios, it's pretty cut and dried. You just need to get the odds ratio, level of significance, the constant, and the R squared, as well as the level of significance for the constant, okay? Because there's two different ones. Yeah, okay. So that's that. In terms of actual interpretation, I got sidetracked. Let me get to my logistic regression output. Okay, so first I want to just kind of like lay this out there because I recognize it is confusing. With regression, with logistic regression, we often will talk about the sort of percent change in the odds, okay? So how we do that is we take odds ratios that are between 0 and 1, and we say those indicate fewer odds, okay? And if you think about this, this makes sense. If, let's say, you know, I have $100, okay, and you had 75% of what I have, you would have $75, okay? So you would have less, all right? You would have fewer dollars than me. If you had $100 and I had $125, I would have greater number of dollars than you, okay? I would have 25 more dollars than you would. And if you had $100 and I had 100% of the dollars that you had, we would have, each of us would have $100, okay? So to get this part kind of like cemented in your brain, think about whenever you see an odds ratio that's less than 1, basically subtract it from 1, okay? So in this case, an odds ratio of 0.36, we subtract it from 1 and get a number of 0.64, okay? We multiply that by 100 to get a percent, and that gives us percent fewer odds, okay? So an odds ratio of 0.36 actually produces 64% fewer odds for us in our regression model, okay? Now, when an odds ratio is greater than 1.00, you simply subtract 1.00 from it, okay? So if your odds ratio is, say, 1.89, you subtract 1.00 from it, and then you have a number of 0.89. I recognize that I left out. Man, I would give anything to be able to write this in right now. Let me see if I can zoom in. Zoom in, zoom in, zoom in. Think it'll just let me throw a little decimal in there? It might. Okay. Oh, I didn't need that one. Okay. All right, so view, zoom out. Okay, so if you have an odds ratio that is greater than 1.00, subtract 1 from it. Okay, so 1.89 minus 1 is 0.89. All right, that's a percent of odds greater that odds ratio is representing. So in this case, 89% greater odds. It's already assuming that it's in relation to something else. So it really comes, I mean, if you really think about it, it's like 189% greater odds. But the 100% is sort of assumed. Okay, I recognize that this has probably not helped you at all in understanding this. And I will say that it is very hard, and I think this is the hardest thing in logistic regression. And half the time, I get it wrong on my first try. So just keep trying, okay? So we think about the 1 as, in this sort of situation right here, standing in for 100%. 189%. So with your odds ratio, almost always you're dealing with a number that's less than 1 or greater than 1. If your odds ratio is less than 1, okay, you simply subtract it from, oh, that's annoying. You subtract your odds ratio from 1 and then multiply that number by 100 to get % fewer odds, okay? If your number is greater than 1, then go ahead and subtract 1 from it and convert to percents. So 1.89 minus 1 equals 0.89. And then you just multiply that by 100 and say, you know, that's the amount of greater odds that odds ratio represents. Okay? You could always just kind of convert these in your head to hundreds %. So instead of thinking of an odds ratio of 1.89, you could just think of it as 189%. And then you subtract the 100% that you would if you were following this model, and then end up with 89% more odds or greater odds. Okay, this is confusing, absolutely. I would say as much as possible, like just try to, you know, it's a two-step process. Like get the interpretation right and then go back and like really work hard to make sure that your interpretation is coherent to a person who's reading your document. Okay, so a fully adjusted odds ratio or a fully adjusted logistic regression. I've got more notes here. Basically, you know, with the odds ratio, with logistic regression, you know, we find that there's two variables in the fully adjusted model that remain significantly related to the odds of having a community level IMR greater than 5.9 deaths per thousand births. Those variables were average % of non-Hispanic blacks and the average % of residents without a high school degree. And again, like the other variables, you don't even don't beat a dead horse here. Just say, you know, not % foreign born, Gini coefficient, and per capita income were not significantly related to the odds of having an IMR greater than national average in the fully adjusted model. Okay, so this is all in a PDF. Hopefully it'll be useful for you as you're working through your regression results. That is pretty much everything I have to say about that. I would say that your regression tables need to be described in 1 to 3 paragraphs. I prefer 1 to 2. You know, a lot of you are going to have non-significant results, so you're going to be able to just say variable blah, blah, and blah were not related to my, the dependent variable. That's completely fine. If that's your situation, then you don't need to write 2 paragraphs. 2 paragraphs is sort of given as the upper limit, 1 paragraph as the lower limit. So that is that. If you have any questions or concerns, please do reach out to me. Otherwise, I'll see you around. Thank you.